Hello everyone. So today in this video we'll explore the landscape of mass spectrometry and understand why LCMS has become such a dominant technique in analytical chemistry. While LCMS is predominantly used in MS, it is important to understand how it compares itself with other techniques like GCMS, MALDI-MS, and ICP-MS, and to understand how other ionization techniques are important for different compounds. So, gas chromatography mass spectrometry was the first widely used MS technique. So, in this, the volatile compounds are separated using an inert gas like helium or nitrogen, and the stationary phase can be capillary coated columns or packed columns. So the key to GC analysis is that the compounds need to be volatile enough that it vaporizes, and it should withstand the temperature of about 400 degrees Celsius. So the principle is that of separation of the compounds on GC is based on its polarity, polarity, and the boiling point of the compound along with its interaction with the stationary phase.
For ionization, GCMS typically uses electron ionization or EI. After the compounds elute from the GC, they undergo hard ionization where high energy electrons bombard the molecules, creating fragment ions that are then analyzed by mass spectrometer. The advantages of GCMS are significant. The chromatographic resolution is excellent, often superior to liquid chromatography. EI produces reproducible fragmentation pattern, which means we can create and use standardized spectral libraries for compound identification. However, the limitations are clear. GCMS only works for gases or volatile compounds with relatively low molecular mass. If your compound decomposes at high temperature or isn't volatile, you either need to derivatize it, adding chemical groups to make it volatile, or you can't use GCMS at all. This is where liquid chromatography-mass spectrometry becomes essential.
So LCMS was only made possible after 1970s with the introduction of atmospheric pressure ionization or API. This was a total game changer because it employed interface for liquid chromatography with mass spectrometry, which was previously impossible because of incompatibility of liquid with high vacuum and MS.
With API, the LC eluent, the liquid coming out of the column vaporizes and ionizes to form gaseous ions, which are then introduced into the mass spectrometer. This happens at atmospheric pressure, not in a vacuum, which solves the fundamental compatibility problem. The most common API techniques are atmospheric pressure chemical ionization, electrospray ionization, and atmospheric pressure photoionization. These are examples of soft ionization techniques, meaning they transfer less energy to the molecule during ionization, producing predominantly intact molecular ions rather than extensive fragmentation. In this picture, you all can see the applicability ranges of these techniques. We can see a chart with molecular mass on the vertical axis ranging from 100 to 100,000 Daltons and polarity on the horizontal axis from non-polar through polar to ionic. GCMS with electron ionization sits in the lower non-polar region, handling compounds roughly from 100 to maybe 1000 Daltons. LCMS with APPI ionization covers non-polar to modulatory polar compounds, also in that 100 to 1000 Dalton region. LCMS with APCI handles polar compounds in a similar mass range. The real power of LCMS comes with electrospray ionization or ESI. LCMS ESI extends from about 100 Daltons up to 100,000 Daltons or more, covering the polar and ionic region. This means proteins, peptides, oligonucleotides, large biomolecules becomes accessible for analysis. Unlike GCMS, one of the key advantages of LCMS is its broad applicability to a wide range of compounds. Once your sample is dissolved in mobile phase, LCMS can analyze even the least volatile or thermally unstable compounds that you could never analyze using GCMS. This opened up pharmaceutical analysis, metabolomics, proteomics, and countless other fields. Now let's talk about matrix assisted laser desorption or ionization. This technique was introduced in the mid 1980s and represents another approach to soft ionization. In MALDI, your sample is mixed with a matrix compound and deposited on a target plate. A laser pulse is fired at this mixture, causing the matrix to absorb energy and vaporize, carrying your analyte molecules with it into the gas phase as ions. This is an extremely gentle process, making it ideal for fragile large molecules. MALDI occupies a space from about 1000 to 10,000 Daltons, primarily for polar compounds. MALDI is commonly used for large molecule analysis like proteins, peptides, polymers, and other macromolecules. The key difference between MALDI and LCMS is that MALDI typically doesn't involve chromatographic suppression. You're analyzing a sample directly from the target plate. This makes it faster for some applications, particularly when you're interested in molecular weight determination or protein identification using mass fingerprinting. However, MALDI isn't typically used for small molecule quantitation in complex matrices the way LCMS is. MALDI excels at biopolymer analysis, while LCMS dominates in quantitative pharmaceutical, clinical, and environmental applications. Now, coming to ICP-MS, that is inductively coupled plasma mass spectrometry, it represents a completely different application space. This technique is frequently applied for elemental analysis. In ICP-MS, your sample is introduced into an extremely hot plasma around 6000 to 10,000 Kelvin, which completely atomizes and ionizes everything. What you're measuring are individual elements, not intact molecules. This makes ICP-MS the gold standard for trace metal analysis, determining toxic elements in environmental sample, measuring minerals in biological samples, and quality control of pharmaceutical for elemental impurities. Now let us see how to choose the right technique. First, what type of compound are you analyzing? If it's volatile, small molecule, and you have access to spectral libraries, GCMS might be your best choice. If it's a non-volatile, polar, or ionic compound, particularly drugs, metabolites, or small peptides, LCMS is ideal. For intact proteins or polymer characterization, MALDI might be more appropriate. And for elemental analysis, ICP-MS is your only real option. Second, consider your sample type and complexity. Complex biological matrices like plasma, urine, or tissue extract are typically better suited to LCMS because you can couple it with liquid chromatography for suppression. Environmental samples for volatile organics work well with GCMS, and elemental contamination screening requires ICP-MS. Thirdly, you need to have practical consideration. GCMS is generally less expensive than LCMS and simpler to maintain. However, LCMS offers more versatility but requires careful attention to ionization, suppression, and method development. MALDI is excellent for high throughput screening but requires more sample preparation. And ICPMS is specialized and typically focused in lab on elemental analysis.
So, the introduction of atmospheric pressure ionization made LCMS possible, and LCMS has a broader applicability, like it can analyze polar, non polar, mid polar, small molecules, larger biomolecules, which is not possible by GCMS. However, each technique has its place. Like GCMS is the workhorse for volatile organics, ICPMS is dominating the elemental analysis. MALDI, it excels in analyzing the large biomolecules. So the best analytical scientists understand these complementary techniques and chooses the right analytical tool to analyze the compounds.
So, this was all about different techniques of mass spectrometry.
Do like and subscribe to my channel if you liked the video, and if you have any question regarding to LCMS, GCMS, ICPMS or MALDI, please do drop it in the comment section. I would be happy to clarify them, and stay tuned for more analytical content.